In school, we learned about Pythagoras Theorem and how it finds the distance between 2 points in two-dimensional space. Although it's quite elementary and we don't need to prove it again, we'll do it for fun here, primarily visually without pen and papers and boring equations. Then we'll explore how Pythagoras Theorem justifies vector components. Most of us are already familiar with these concepts, but understanding these fundamental constructions will later enable us to derive the visual representations of the inner product from Pythagoras theorem and vice versa, which you may not be completely familiar with. So let's begin this boring presentation. Suppose we are trying to find out the length of this particular line. That is, we are trying to find out the distance between these 2 points. Then in R2, we will use the Pythagoras theorem to find out the required distance, which states that in a right-angled triangle, the square of the hypotenuse side is equal to the sum of the squares of the other 2 sides. Now we will prove and use the Pythagoras theorem to find out the length of this line or the distance between these 2 points. And to do so, we will construct a right-angled triangle by making the line as its hypotenuse. Let the length of the hypotenuse be C, and the other 2 sides of this triangle are A and B. Here we will prove this theorem with visual appearance instead of using trigonometry and calculations. That's why, for future reference, let us sort out those lines which represent the sides of the triangle with length A, B and C. Now let's make copies of the triangle and rearrange them in such a way that it forms a square. And we fill the square with white color, which is not covered by those triangles, and then again make a copy of the whole square. Now within the left side square, we rearrange those triangles in such a way that the region not covered by those triangles is separated into 2 parts. And we can see that one of those regions is inclined with the sides of 2 triangles having length A, and the other is with the sides of 2 triangles having length B. And eventually, those 2 regions are squares having side lengths as A and B respectively. And that's why the area of the left side square, which is not covered by those triangles, can be expressed as a sum of 2 squares having area A square and B square, and that is equal to the area C square, which implies C square is equal to A square plus B square. And we can verify it again by constructing a triangle having sides of length A, B and C respectively. And this is the Pythagoras theorem, which further gives us the length of the line as C, which is equal to square root of A square plus B square. That's how, if we have a right-angled triangle having sides of length A, B and C, where the line having length C represents the hypotenuse, then we have C is equal to square root of A square plus B square, which is in fact the distance between the origin and the point P having coordinates AB in 2-dimensional space R2. Here the point V basically is a vector in R2 emanating from the origin and terminating at point AB. And that's how C determines the length or norm of the vector V to a square root of A square plus B square, which has coordinates AB. And let's think about this representation from a physical aspect. So first, let's place a ball at the origin. And suppose a force F can displace a ball by length norm v. Now if we apply that force on the ball along x-axis, then it will displace the ball by length norm v horizontally from the origin. And therefore, the coordinate of its center will be norm v0, which in fact indicates the displacement along the y-axis to be 0. In other words, if we apply this particular force along x-axis, instead of having a certain displacement along that, there will be no such displacement along y-axis at all. Remember, we have considered the space R to have only two independent directions, and those are along the unit vectors of standard basis. And on top of that, we can express all the other directions as a combination of these two directions. Here basically, we are considering only these two directions are independent. That means all the vectors along those two directions have no components along any other direction. And that's why, if we apply the force along y-axis, then we'll have no such displacement along x-axis, but we'll have norm v amount of displacement vertically. Therefore, its coordinate will be 0 norm v. Now suppose we are applying that force along the direction of vector v, then the ball will be displaced from the origin to vector v itself. And along x-axis, the displacement will be a, which is basically the length of projection of vector v along x-axis. And if theta be the angle between the vector and x-axis, then basic trigonometry will give us a to be equal to norm v cos theta. Similarly, the displacement along y-axis is b, which is the length of projection of vector v along y-axis. And here b is norm v sin theta. Here since the force vector F results in the displacement of the ball by a certain amount of distance, here which is norm v, therefore we can simply represent all those vectors by certain amount of displacement in a certain direction. Now in two-dimensional space R2, if we want to displace a ball from the origin to v, and we are only allowed to travel along two axes, then to reach at v, we have to displace the ball by length a along x-axis first from the origin, and then from there, we have to displace the ball by length b along y-axis. And it is equivalent to apply two forces respectively, responsible for those two displacements. And since a vector has no specific position and it only has magnitude and direction, that's why we can think a vector emanating from the origin and then displace that vector accordingly. And that's how we got two components of the vector f along x and y axis, which are f cos theta and f sin theta respectively. And by a simple calculation, if the force F is responsible for norm v amount of displacement, then norm v cos theta amount of displacement will be done by force F cos theta. Also a similar result holds for F sin theta. And these all together validate the conclusion. Now when we apply any force in any arbitrary direction on two-dimensional space, then the force has two components. And those two component forces together act on the ball to displace. And the displacement will be same as if the resultant force has acted on it. And that's how, here by the force vector, we can simply have an intuition how the vector addition actually works and how the projection plays a crucial role on it.